is we've been calculating in class the theoretical yield. So that's all of our calculations that we've been doing. So if our starting reagents are all used up, if our limiting reagents completely used up, we can theoretically produce a certain amount. In reality, that doesn't always happen. So there are many reasons why a reaction might not make as much product as expected. We might have impure reactants. I don't know if any of you bothered to look on any of the bottles we were working with, but lots of them have purity percent. So if we're working in an analytical lab, they would want their reagents to be 99.99% pure. But because that costs more money to buy those reagents, we don't always get that pure of reactants. We might have errors in our experiment design or maybe equipment errors. We could also, this happens a lot in organic chemical reactions, so synthesis of pharmaceuticals often don't go 100% the way you want them. So just by nature, the reaction doesn't proceed 100% the way you would expect or want it to, or there might be some side reactions that happen. So those are all reasons why our theoretical yield is not exactly the same as what actually happens in the lab. So we've already been using this formula a little bit, right? We did 2 labs where we did kind of a percent yield. True story? No one wants to talk because they don't want to be on the YouTube. Percent error, we haven't really used this calculation. We've just done, if everything went 100% right, we just subtracted our percent yield to get the percent error. You guys kind of remember doing that in that last lab? The malachite lab.
Oh, yeah.
We could also put it in this formula. So the difference between our theoretical and actual divided by our theoretical yield and times by 100% is another way to get our percent error. Kind of make sense? Okay, so these are strict problems just like we've been doing them, but they're also asking for percent yield. So we're going to figure out our theoretical yield, which is essentially what we've been calculating with all of our strict problems, and then do one more step. So that's what these are doing. These questions are. I don't know, which one do you guys want to do? We'll just do one. And these look particularly tricky to you that you... The first one? Okay. The most words. All right, so we'll read our question for first. During the manufacture of cement for the construction industry, mined limestone, which is calcium carbonate, is thermally decomposed to lime, which is calcium oxide, and carbon dioxide. What's the percent yield of the reaction when 13.1, what's this big M?
Don't have what I mean.
Big M.
Grams per mole.
Megagrams of calcium oxide are obtained from the treatment of 24.5 megagrams of limestone. So this probably seems a little confusing, but it's a strike problem. Where do we start? Balanced equation. So we're going to write out our balanced equation. What are we reacting? Limestone. Which it's formula
CaCO3.
CaCO3.
Arrow.
Ca. CaO.
Oh crap.
It tells us it makes this and this. CaO and CO2 gas. If we're getting really fancy, because it tells us this is happening by thermal, we would put a little triangle above our arrows saying that we're adding heat. So we're heating this up. But it doesn't really help us with our strike problem at all. And Katie is saying it's already balanced. So all 1-to-1 ratios, which is nice. let's write down what we know. So this is where students get a little bit tricked. What number are we using in our stoic calculations? Are we using this number or are we using this number? Because only one of them is going to be used when we do our percent.
The second one. No, it's the second one because if you're saying you have that much of one product, there was one thing, or
Use the second one because it says you get the first one from how much of that one.
oh yes, I do.
Okay, so this is what is obtained actual. So this is the actual yield. So 13.1 megagrams of calcium oxide, that's our product. And if we want to know percent yield, we're doing that with our product. Does that kind of make sense? So this number, the 13.1 megagrams, we're going to use it when we calculate our percent yield. We're not going to use it in our stoic problem. Because this is where students get confused. They write down this number under calcium oxide, and they write down this number under calcium carbonate, and then they don't know what the heck to do. Are you with me? Hopefully. Okay, so we're going to write down this 24.5 megagrams. So that's how much limestone they're starting with in this one particular industrial reaction, and then they want to know what the percent yield is if this is what they actually got. So what are we trying to figure out before that?
We need the theoretical.
We need the theoretical yield. So where are we putting our question mark?
Under the sea.
Under the CAO. So what else do we need to do these stoic calculations?
Don't you want it in grams, not milligrams?
Let's do it in megagrams.
Well, you know, the,
So, I'm lazy, as I tell you all. Since this is already in megagrams, our actual yield, and this is in megagrams, why not calculate our theoretical yield in megagrams? And then we don't have to do
Grams per mole, not milligrams per mole.
Okay, I'll show you a little trick. So we're gonna make our goal megagrams. So what else do we need? The grams per mole. So someone want to calculate the grams per mole of calcium carbonate, and someone can calculate the grams per mole of calcium oxide. Don't all grab your periodic tables at once.
The calcium oxide is, oh, hold on. Are you doing all of it? Oh, the first one is 100.09. And then go to 40.08. Plus 60.00. And the other one is 66.08. Oh, yeah, yeah.
Is this a limiting reagent problem? Nope, because we just have one reactant, so that is going to limit how much products we can use. So I'm going to show you a trick, Sam. The answer is no, you don't have to, but if you like doing more work, you can do more work. You can fully do more work.
Wait, what is it?
Again, we're not liking this mega.
Oh, okay.
It's just a prefix, right? It just tells us we have 10 to the 6 grams.
Why don't we just take the answer?
Because we're gonna be lazy like your teacher. Okay, so we're just gonna keep this mega. It's a prefix. We have 24.5 times 10 to the 6 grams. That's what a megagram is. So, do people remember that? And if you don't, if you turn to, in your data books, if you turn to page 3, it has a little legend about what all these prefixes mean. So you don't have to memorize them. So the giga is 10 to the 9. So instead of using scientific notation in these numbers, this is just telling us how big this number is.
Oh my god.
Are you going to lift, Katie?
No, just still under the sun.
Suffixes go at the end. Prefixes go at the beginning. Okay, well, we're just gonna leave the M. I know it's gonna hurt you guys, but it really won't in the end. Okay, so we're gonna take this megagrams and we're gonna convert them to megamoles. So how do we convert in general grams to moles? Divide by molar mass. So we're gonna do our, oops, and let's write in a pen. 24.5 megagrams over 1. And then we are doing what with our molar mass to get rid of grams? We're gonna flip it. Divide by 100.09 grams per mole. And we'll write what type of moles they are. Calcium carbonate.
So you don't have to convert grams per mole to megagrams.
No, you don't have to convert the grams per mole. You don't have to convert the megagrams to
And
grams.
if it's kilograms, you do the same thing.
Yeah. So what happens to our units? What is canceling out?
The grams.
Just the G's. G's divided by G's. And we have megamoles. So that prefix, that big letter M, 10 to the 9 is just hanging out.
And then next we'll put here.
So our next step, we want to convert,
No, we're baby step people.
No, we're not.
You're the only one who isn't baby.
And you guys.
We're not baby people.
okay, I'm going to do non-baby step because otherwise I'm going to run out of the room. So we're going to convert moles to moles of calcium carbonate, moles of quinoline to moles of unquinoline. So our ratios are 1 to 1. So for every 1 mole of unquinoline
not write that.
calcium oxide, we require 1 mole of calcium carbonate. So now what's canceling out? So moles of calcium carbonate over moles of calcium carbonate are gone. And we've got mega moles of calcium oxide. Our goal is megagrams. So how do we get rid of the moles?
And to the 56.08 to multiply it.
Perfect. We're going to take this 56.08 grams over moles, and we're multiplying it. So we've got moles divided by moles canceling out, and our units are megagrams of calcium oxide.
Answer, do you know what the answer is?
So it's megagrams.
It's 14.2168.
So we can enter this in our calculators all in one go. Katie's got a number already. But for the benefit of the people not here, we're doing 24.5 divided by 100.09 times by 1 divided by 1. Don't need to do that. Times by 56.08. And is that what you got, Katie? 13
Nope.
point.
I got that one.
What the heck?
No, I think it's.
I didn't
I got
baby steps,
14.
I got
It
that.
shouldn't change things if you do things in baby steps. 24.5 divided by 100.09. There's your first baby step.
I literally put the exact same thing in my test.
If you times by 1 and divide by 1, I mean, that's not going to change anything.
Oh, no, I didn't.
And then our last step, we're multiplying those megamoles by 56.08.
I put 68.08, not 56.
Ah, so we've got to enter the same numbers. And we get 13, so this is non-baby step, 13.727, and baby step 13.727.
So that's in grams then.
This is in megagrams.
So then we're gonna do what I actually yield over to that yield.
So 13 point, and significant figures, there should be how many?
3.
So it's 13.77.
Is the theoretical yield the one we're doing?
Yes, megagrams of calcium oxide. So this is our theoretical yield.
Oh,
Yes.
did you not chemicals?
Nope. So there's our theoretical yield. Our goal after that, they want us to figure out the percent yield. So we've got a formula for that. Here's our formula for percent yield. Actual over theoretical. So our actual is what?
13.1.
13.1. So our percent yield is that 13.1 megagrams divided by 13.7 megagrams and times by 100.
It's 95.6.
And check out our units, so being lazy pays. Megagrams are gone over megagrams, so instead of doing 2 conversions to get rid of megagrams and have grams, we saved ourselves 2 steps. But if you really don't like the big letter M, you could have done this by multiplying this by 10 to the 9. And that would have gotten you grams. Oh, 10 to the 6, yeah, sorry, 10 to the 6. And multiplying this one by 10 to the 6.
So because it's not fun.
But it seems like more work to me. So I don't like more work. Okay, so I think that's all we got.
Let me see the percent error.
Did it ask for percent error?
Well, no, it said percent yield.
It didn't ask for percent error, but that's a good point. What would our percent error be?
How did you figure out the last?
Well, wouldn't it be 95.6% divided by?
I don't know what to mean.
So we could just subtract 100 from this to get our percent error, or we could do theoretical, our 13.7 minus actual, which is 13.1, divided by theoretical, and we get the same percent.
Subtract that from 100.
To get our percent. So if this is what you got, right on the test, Katie, how would you figure out what percent you got wrong? That's kind of what percent error is how much you got wrong. Does that make sense?